Alright guys, today we're going to be talking about equilibrium. Okay, this is the last part of the unit on the factors. And there's a different type of reactions here. And we've done in the past, your general five types of reactions that we've done in the past. And in this case, things get a little wild. It's going to be light this week, probably going to introduce this to you guys, and then next week, we'll get into a little nitty gritty of it. But just a quick introduction to something called equilibrium. And in the past, many reactions that we've encountered in the past generally go to completion. And when reactions go to completion, what's going to happen most of the time is that you're going to go and the reaction is going to end after the reactants form products. Okay, and eventually one of those reactants, or both if you're lucky, are going to run out to produce products. And once that happens, the reaction ends. And that's when a reaction goes to completion. Good example is when you cook. You finish your recipe, you baked your cake or whatever, and then then the reactants are finished, they form products, and the reaction's over. Okay. Good example is something that forms a precipitate. Now, on your note sheet, you might see this a little different. This should be a single arrow, so make sure you make that change. Okay, so a good example is a precipitation reaction where you form a precipitate, and once that precipitate forms, the reaction ends. Right, it doesn't go on forever. Same thing with combustion. When combustion burns with a fuel, all right, once this fuel methane is done, the reaction ends, okay, and this would be done. So these are two common reactions that would form a completion reaction because the reaction is finished after those reactants react to form products, depending on the amounts. Okay, however, sometimes reactions can actually reverse themselves and go backwards. Okay, and this is while they're going forward. So there's a little bit you got to think about this a little. So let's say we made ammonia and we had 3 molecules of H2 and a molecule of N2, and they were going to react in a tank to form as gases. These are going to be gases now to form NH3. Well, what happens in this case is that NH3 in the same tank as these other molecules will actually collide in the tank as well. They're going to be all there together. But in this case, what those NH3 molecules can do is they can actually collide and then reform and break back up into N2 and 3H and these guys again, and 3 molecules of H2. And then those can recombine to form NH3. And really this reaction can actually go back and forth until it reaches some type of balance where the speed at which you create NH3 is the same speed as if this breaks apart into 3H2 and N2. Okay, and when it reaches that point and both are created at the same speed, that would be something called equilibrium. You've reached some type of balance. Okay, so what's happening at this point? Well, a few things actually. The reactants and products are both present, okay, and continue to react, and that's really important. Okay, if you looked up here at in these two reactions above, you'd find that the precipitate, once that forms, one of the two reactants goes to zero. When you burn a fuel, the reaction stops when you run out of the fuel. But in this case, you're not going to run out of any of these guys. They're going to continue to react forward and reverse. So we're going to call this the forward reaction. We'll call this the reverse reaction, and that's how we want to do it. Okay. Next thing is concentrations. The amounts of both of these will stay constant over time, which means once this reaches a balance, you'll have the same amount of NH3 present that you would the other two gases. Okay. What we do is we usually identify this by looking at a double arrow. So you'll see a double arrow versus a single arrow that you'd see in a completion reaction. Okay, and I like to think of a good example. I'll do really quickly on this. Is a city A and city B, and let's just say city A and city B were separated by a little river here. Okay, and you wanted to visit city A and city B, and one day city A decides they're going to build a little bridge over to city B, and city B is going to build a return bridge back to city A, and they want to visit each other. Okay, and you wouldn't be allowed to be in here. This is a deadly ocean or sea or lava pit or something where you cannot be in here. All right. Well, let's just say city A decides to let cars go over the bridge, and we have a little car here, and we have a little car here, and a little car here. Okay, and we start letting people drive over the bridge in that direction. And we do the same thing on this side for city B. City B allows people from city B to go to visit city A. So we have little cars. Right. There's these little cars. These cars are going to go that way, and these cars are going to go that way. Okay, let's just city A has 100 people. Okay, and city B has 200 people. Whoops, make sure, let's make it 350, why not? Okay. Now, as long as the cars going forward in this, forward going this way are the same as the cars going in reverse at the same rate, as long as they keep going back and forth between the two cities, the 100 and the 350 will do what? They'll actually remain the same right over time, as long as the rate at which they change is equal. Okay, and that's the important thing to remember about equilibrium is it's really important that what you see in the word equal is really the rate of change. Okay, it's the rate of change of the cars going back across here, or it's the rate of change of these molecules. Okay, the amounts don't have to be equal because obviously 100 people and 350 are going to be different. So you don't have to have the same amount of NH3, the same amount of N2, the same amount of H2. You just have to make sure they're present and they're constant over time. Okay. Now, what happens in this case is if you have an accident, let's just say you have an accident and you change, and there's a hole in the bridge, say here. If there's a hole in the bridge here, then the forward reaction here this way is going to slow down. Okay. And if that changes the speed of this reaction and doesn't change the speed of the reaction above it, then these two numbers will change, right? That's what's going to happen. So eventually, as cars don't arrive at city D, this number will go down, but people could still arrive at city A, so this number will go up. And now you've destroyed the equilibrium. Okay, so that's the important thing to know about equilibrium in general. All right, next slide. Okay, so basically, equilibrium is going to exist. Okay, and this is what the definition is: when opposing reactions or changes occur at equal rates. So it's really equal rates of change. That's what you want to think about when you think about equilibrium. Okay, so that's really important. Okay, and so if you get into like the actual specifics for chem, the concentrations of the reactant products are going to remain constant, but not necessarily equal. I mean, can the populations of both cities be the same? Yeah, I guess they could, but that's going to be coincidence more than anything else. All right, so the concentrations are going to remain constant, but not necessarily equal. Okay, you got to be in a closed system. Okay, that's important to know. You can't have molecules going in and out of the system. The system has to be contained. All right, you're going to be very temperature dependent here. We'll go over that a little bit later. Okay, and if you ever see concentration, if you ever see these X in parentheses or any type of molecule or any type of compound that's in parentheses, like this in brackets, I should say, that means molarity. Okay, that means concentration of molarity. So if I was to go, if I would put brackets H2, all right, that would simply mean I would mean concentration of H2 in molarity. Okay. All right, next. Okay, things are dynamic. They're going to be changing each time. Okay, molecules are going to be colliding, they're going to be crashing into each other. They're going to be doing chemical changes, but there's two different reactions, okay, that are taking place in opposition. Okay, so things are happening that way. Okay, there's basically three different types here that I'm going to show you here before we do the actual chemical changes. Okay, and this is more of something called phase equilibrium. It's a type of equilibrium where it happens during phase changes. So if you are stuck at 0 Celsius for water, you're going to have an equal rate of change as things melt and freeze at the same rate. So ice cubes here will be melting to form liquid water, and liquid water will be freezing to form ice cubes at the same rate. Okay, at the same speed. So you really wouldn't see a difference between the water and the ice cubes at this point, as long as you kept it at 0. Okay, so the way you would write that would be water is a solid plus heat, okay, because you need that to melt, correct? So it'll be on the left side. All right, and that would create liquid water. Liquid water would then refreeze backwards to form solid again. So really looking at ice becoming liquid water and water becoming ice at the same rate, okay? And of course, heat would be absorbed and released at the same time, considering you're keeping this at 0 Celsius. Think of this here in phase and solution equilibrium, and this part of it. Think of this as maybe a can of soda here. Okay, maybe a can of soda that's closed. Okay, again, we're talking about a closed system here, a closed system here. Okay, and what's happening inside here is your liquid, your AQ here is down here, but above that, in the space above the liquid, is carbon dioxide gas, and that gas is going into the cola and outside the cola. And this continues to do this back and forth. As fast as that gas is going into it, it's releasing. So this reaches a balance. Okay, so if you were to write this, you would say gas is in equilibrium with its AQ, and the EQ is in equilibrium with it's gas. All right. Now, of course, you can go ahead and pop the top, but if you pop the top, that means the gas is going to be formed in that direction faster, and then the gas would be coming out, and you would no longer have equilibrium anymore. All right. So again, you have to satisfy everything above here, all the stuff above here, to be at equilibrium. Okay. The last one is a special case called a saturated solution. A saturated solution is when you have sodium chloride crystals, all right, that dissolve to form the AQ version, and then the AQ version turns around and forms crystals again. All right. So again, over time, you would not be thinking about these crystals; they would be sitting there doing nothing. But if you looked under fine magnification, you would find that they would be dissolving and crystallizing at the same rate. How would you write this? Again, with a double arrow. You would say solid crystals are forming AQ, right? Those are bouncing around and moving around the container and swimming around the container. And then those two, when they combine again, they're going to turn around and go backwards again and form the solid. Okay, but this is only happening when you hit the saturation point, which has to be defined at a specific temperature. At a specific temperature, at a specific temperature is temperature dependent. Okay? So again, a way you can define equilibrium in some examples. Okay? When you're in chemical equilibrium, that was when we looked at the ammonia reaction before, and you have a situation where you're doing a chemical reaction. Okay, a chemical reaction is going to do this too, and sometimes it's a good thing and sometimes it's a bad thing. All right, so really just as a reminder, at equilibrium, the rates of the forward, okay, and this is the key, the rates of the forward and the reverse reactions are going to be equal, but the concentrations are going to remain constant, and that's really the definition really of equilibrium. Okay, so we're going to remind you of that. Okay, but what if, and the key is equilibrium can be quite boring. Okay, I know Mr. Russo's not too boring. I know I'm never boring, but only kidding. But equilibrium, since it's such a balance, you really kind of don't notice that it's happening because it's kind of like it's dull, it's kind of boring. So what's more interesting is if you disturb the equilibrium, and you can disrupt it, okay, by adding a stress to it. You can stress it out. And what's interesting is that equilibrium will react to you. Okay, something will happen as a result of the stress. Just like when people are under stress. When people are under stress, you react to it. Okay. All right. So you could look at these kind of pictures. Are kind of funny. I did not know that when you spell dessert backwards, it's stressed. By the way, so that'll help get rid of some people's stress is having dessert. Okay. And a little stress picture for you. Okay. So some types of stresses that you can do to a reaction that would cause some type of disturbance. Okay, and you probably could think about these on your own. For the case here, we'll think about it. Okay, temperature is a good stress, right? If you increase the temperature or add heat or heat it up or cool it down. Okay, a change in concentration, the number of particles, the number of moles, right? How much you add to a system at equilibrium is a stress to the system. Okay, and again, that system is gonna be stressed by this. Okay, increasing the pressure for a gas. All right, we talked about Boyle's law, right? If you have a gas in a container and you put pressure on it, what does that container do? It's got to get into a smaller volume, right? It reacts to your stress, right? Reacts to the stress. Okay, so these are the kind of things that also affected what? They affected collisions. Okay, and if you affect collisions, okay, then you are going to affect the reaction, right? And that's going to be important going forward, what we're going to do here. All right. So one thing to remember here, really, really important at the end, is you may think that, hey, I can speed up my reaction. I can change it. I can change this by adding a catalyst. But think about this. What a catalyst does is it lowers that height of that hill. It lowers the activation energy. So if you're lowering the activation energy, you're really doing this for both the forward and reverse reactions. Okay. So if you affect both forward and both reverse reactions at the same time, then you really don't stress the system. You just simply make the reaction in both ways faster. Okay, and that just reaches equilibrium faster, just like the cars going over the hill. If you increase the speed limit of the cars going to city A to city B, the same speed limit as city B to city A, then those populations in both cities really don't change. People just go back and forth to the cities faster. Okay, so that's the key. All right, so you got to remember that. All right, so then we define what happens as a result. Okay, and people do this too. All right, we get stressed also. So we want to define a scientist, a French scientist, Le Chatelier. What he did is he worked on doing work on this and realized that when you stress a system, If you apply some type of stress to a system at equilibrium, what the system does is respond, okay, to reduce that stress or remove that stress or counteract that stress. Okay, and again, this is something we do all the time. Even now during this crazy time, what do? We react to stress. Like stress is placed on us, okay, and what do? We respond by doing something about it to try to remove that stress. Well, reactions are the same way. Nature is the same way. Nature will react in a way to remove that stress. Okay, and that's what Le Chatelier's principle means. All right, so just some little things that you probably experienced that in your own body or around you that would be Le Chatelier's principle. And really, let's just say you get a new pair of shoes or a new pair of boots or skates or sports equipment or whatever, and you end up getting a blister. Everyone's got a blister before. Well, what is a blister? A blister counteracts a sore spot on your skin, right? So if it's rubbing in a weird spot and it's a soft skin, your body reacts by giving you pain, or it reacts by giving you a blister or some type of callus to, remove that stress upon it. Okay, a thermostat in a house. Okay, it's getting warm out finally. You might be turning on the air conditioner. Why? Because as the heat in the house rises, you want to. It's stressful. So what happens is the thermostat switches on the heat. It's set at maybe, let's just say the thermostat in your house is set at 70. Well, if the house, reaches more than 70, what happens? The thermostat switches on, the AC comes on, and that drops the temperature. Correct. So it happens when it's hot or cold. You can have that thermostat switching on to remove the heat or remove the cold. Okay, and last but not least, this is more of a personal thing. People react differently to stress factors. What do? They can cry, they can yell, they can scream, they can punch the pillow, they can, eat, they can. People do all sorts of crazy things, but most of us would have to get rid of the stress. Some people exercise, some people take a hot shower. It depends on the person, all right? But what's the key? The key is you want to remove that stress. Okay, so we're going to do a little bit more with this next week. Okay, we're going to show examples of Le Chatelier's principle, and also how we can use this to our advantage. All right, so we can manipulate reactions at equilibrium to do what we want them to do, and in that case, make things real interesting. All right, so I'm gonna sign off now. Quick week this week. Just make sure you do the CASA learning. We're going to keep it real light. Okay, and have a great day.